All right, so the first problem is the definition of mathematical induction, or I would say the theorem of mathematical induction, okay? The definition, the theorem. And use mathematical induction to prove inequalities. Okay, so the statement of the theorem of mathematical induction, you can check your notes, and also the problems would be similar to your first exam, okay? You have a inequality which you need to use mathematical induction to prove it. Of course, this inequality would be about natural numbers. Okay, so I'm not going to give an example because these are going to be similar to the problems in the first exam. Okay. So the second problem would be about definition of union, intersection, complement, of sets. And prove properties of intersections and unions of sets. All right, so this the second problem is about sets. So first we have to know the definition of union, intersection, and complement of sets. And also you need to prove, for example, like one of the De Morgan's law, or some of the properties we talked about in class. So essentially you just need to use the standard procedure to prove two sets are equal. So left side equals to right side. So you want to prove the left side is a subset of the right side, and prove the right side is a subset of the left side. Then you can claim these two sets are equal. So prove two sets are equal. Okay, so this problem clearly appears in your second exam. So you just should look at those properties we talked about in class. So look at your notes and also review your second exam. All right, so the third problem is about rational and irrational numbers. So the definition of rational numbers and prove a given number is rational or irrational. Okay, so what is a rational number? So a rational number, Q, the notation is set of all number x, so that x is equal to m over n, where mn are integers and n not equal to 0. So the set of all rationals are just quotients of integers with denominator non-zero. And of course, you may have different representations of the same rational number. For example, 0.5 is equal to 1/2, or 2 over 4, or 3 over 6. Okay, so there are many different representations, but the equivalent representations would just mean the same number, one number. So we should understand it. Okay, let's look at an example of this type 3 problem, for example. So we want to prove square root of 7 is irrational. How to prove this? So normally when you want to prove something is irrational, you do have to use proof by contradiction, because we only have a clear definition of rational numbers, but irrational numbers, just what we stated is that those real numbers which are not rational are called irrational. So there's not an explicit definition of irrational numbers. Instead, we only have an explicit definition of rational numbers. So normally we use proof by contradiction. Okay. So proof by contradiction. All right. So we suppose square root of 7 is rational. Okay, if square root of 7 is rational, by definition, we can write square root of 7 is equal to some m over n. And of course, one key assumption here, as I said, a rational number may have infinitely many representations of the form of the quotient of two integers, but we may assume by cancel out the greatest common factor of m and n, we may assume f and m and n are co-prime. And we can assume the greatest common divisor of m and n is equal to 1. Okay, so this is very important here, because if you don't specify which representation you are using for a rational number, then later the proof runs into trouble. So we want to reduce this quotient to the simplest form. So that is the greatest common divisor of m and n is equal to 1. They're co-prime. All right, so let me continue to the next page. All right, I'll copy it down. So this is our assumption. So assume root 7 is equal to m over n, and the greatest common divisor of m and n is equal to 1. Okay. So now what we're going to do is to square this equation. So square the equation. And we get 7 equals to m squared over n squared. All right, so you multiply n squared on both sides, you get 7n squared is equal to m squared. Okay, here you can see that this tells you what? M squared is a multiple of 7. So this implies 7 divides m squared. Okay, because m squared is equal to 7 times n squared. So m squared is a multiple of 7. That means 7 divides m squared. All right, now we need to recall a lemma for the divisibility of prime numbers. 7 is a prime number, and 7 divides m squared. That is 7 divides m times n. And the lemma, recall the lemma tells us if a prime number divides the product of two integers, then this prime number must divide one of this component. So this implies actually 7 has to divide n. Okay, so this is a lemma, so recall the lemma. Recall. So if P is prime, and P divides A times B, and P divides A times B, then either P divides A or P divides B. But in this case, you see m squared is m times n. Both A and B are n. So 7 divides m squared would imply 7 divides m or 7 divides m. So in any case, 7 divides m. Okay, so this is the lemma we use in this step. All right, so since 7 divides m, we can write m is equal to 7 times k. Okay, this is definition of divisibility. M is 7 times k. Now we're going to plug in to this identity to this equation above. So what do you get? You get 7n squared is equal to m squared now is 7k. M is 7k squared. Okay, so next we get, we just expanded 7n squared is 49k squared. So you can divide the 7 on both sides. You get n squared is equal to 7 times k squared. Now we are in a similar situation as above, because this time we get n squared is equal to 7k squared, which means n squared is a multiple of 7. That means 7 divides n squared. Again, we use the lemma we just mentioned. This implies 7 divides n. Okay, now if you see what do we get? We get 7 divides n and 7 divides n. So these two things would imply the greatest common divisor of m and n would be greater than or equal to 7, because 7 is already a common factor. So the greatest common factor would be bigger. So this is a contradiction, that this contradicting this assumption here, because we assume the greatest common divisor of m and n is equal to 1. Okay, so this finishes the proof, because this means that the square root of 7 cannot be irrational numbers. So at last, this implies root 7 is irrational. Okay, so any questions about this example? Okay, so let's continue to the next example, next problem. So problem number 4 is the statement of the Bazal's lemma and lemma for Euclidean algorithm. And use Euclidean algorithm to find the greatest common divisor of A and B, and express the greatest common divisor of A and B as a linear combination of A and B. Okay, so this would be a problem similar to the third exam you just took. Okay, the examples and the notes are essential. You just read your third exam and your notes, it would be enough. And the last problem is the statement of the fundamental theorem of arithmetic. And find the least common multiple of two numbers A and B. Also, the last problem is similar to the problem in your third exam. So we don't need to talk more about this about this problem. Okay, so those are all the problems we're going to test for the final. I think if you reviewed your first, second, and third exam and your notes, there should be no problem to get a good score for your final exam. So is there any questions about this all the problems for the final? Oh, no. So because the Chinese remainder theorem is a optional topic, it's difficult because that's only for your interest. If some of you will go to graduate school, I'm not sure, to do number theory, whatever, so this would be something definitely you need to know, but we're not going to test it. Mm-hmm. Any other questions?
No.
All right. So if you don't have any other question, we'll stop it here today. And Thursday, next Tuesday, if you have question, then you can come to the question session. Or if you don't have question, then we'll meet on November the 24th, I think, the exam date. All right.
Thank you.
Bye-bye.